Hi, power electronics is very important when we model electric vehicles, especially when we start modeling inverters and converters. Therefore, today today we are going to focus on fundamentals of power electronics. I do know the power electronics is the use of electronic devices to control and convert electric power from one form to another. And we are going to focus on three main sections, that is rectifiers. They know that rectifiers they change AC to DC. Those are rectifiers. Inverters they change DC to AC. Those are inverters. Converters also change AC to DC, but most converters use thyristors. Rectifiers use diode, while most of the rectifiers use diode. And most of the inverters, most of them use MOSFETs, IGBTs, while the converters use thyristors, most of them. Then rectifiers, most of them use diodes. We have said rectifiers change an AC to DC, and most of them use diodes. Converters, most of them use thyristors, and still converters change AC to DC. Also, we have some scenarios whereby the converters change DC to DC. Okay, our main focus today in this video, we're going to focus on rectifiers. Rectifiers that rectifiers, and we usually have two types of rectifiers. That is uncontrolled. We have uncontrolled rectifiers and controlled rectifiers. In controlled rectifiers, we have three types. We have full wave rectifiers, half wave rectifiers, and single stroke three phase rectifiers. And let's start with a half wave rectification. It's very important for us to understand this concept because we are going to model the control system of motor. We are going to control DC motors, permanent magnet motors, and we'll be using most of these. Okay, therefore, let me start. That's better. Okay, whenever the inverters, rectifiers, and converters, whenever they are functioning, they use a solid state switches. And we have various types of solid state switches. Some are as seen diodes, and we have said most rectifiers use diodes. We have resistors, whereby most converters use resistors. MOSFETs, IGBTs, and GTOs, they are mostly used by inverters. We are going to see in a near future video as we control a DC motor using a MOSFET. And this MOSFET, we have another called silicon carbide MOSFET. The difference between this MOSFET and this MOSFET, this one is a purely a silicon MOSFET. This one is a silicon carbide MOSFET. You can do some research and see the differences. Okay, therefore we are going to use a half wave rectification. We are going to use a diode in half wave rectification. Okay, Let's now start. We're going to use an AC. Remember, you have said rectifiers change AC to DC, therefore we need an AC power source. Then we need a diode, then we need a load, and we need a means of measuring the voltages and do the comparison. Therefore, the first block we need, remember as I said, we'll be using a simscape. Then for the simscape, we are going to use electrical. In the electrical, we are using specialized power systems library. Today this will be our main focus. We need an AC source, therefore I need a source. Okay. Under the sources, we can use an AC current source or an AC voltage source. Let me use an AC voltage source. Since it is an AC, we have to use RMS, therefore it is 230 multiplied by SQRT of 2 to get RMS. That's the peak amplitude. The frequency, let me use 50 Hz, then okay. Therefore, just 230 voltage. We need a diode. Therefore, we go back to library, go to power electronics. In the power electronics, you're going to get all those types of switches. You can see there are very many MOSFET, thyristors, IGBTs, GTO is here. Okay, therefore, let's use a diode for now. We are not measuring anything. Double click on the diode and take measurement port. Okay, we just need to control the current flow back and forth. Okay, therefore you connect this AC to the anode. We have an anode and we have cathode. Therefore we connect this is forward bias when you connect this one at this port. If you connect this at this point, it becomes a reverse biased. Then we need a voltmeter to measure the voltage so that we can do the comparison. Go back to library, sensors and measurements. You select, we need a voltage measurement here. Okay. Then we need a load. For us to have some current, we need load. Go back to library, use passive. I'm going to use a resistor load here. I have selected RLC branch. We can rotate. I want to use R only. I want to use 230 by 5 as my resistor. Okay, this is my load. You connect to one side of the diode. If you want to see the word diode, if it keeps disappearing, right click on the branch, you go to format, you show block name on. Now you can be able to see this block is a diode. Then the side on negative side of the battery, the power source, sorry. Therefore we need positive side and a negative side. We need a scope to display the measured values. We also need a voltage here to measure the voltage across the resistor. This one is R. Therefore, you can copy this, you connect it here. Okay, then you connect V to scope. We also need to measure this, that is the input. That's my input. Let me put it there. We also need to measure the current. Therefore, I go back to library. You go to sensors and the measurements. You select current measurement. You delete this that branch. You connect these two. Remember, I said always connect to a current sensor through the through while the voltmeter is across. You can check that video how we discussed types of variables used in Simulink. This is my current here. We have a current measurements V in. Make it a habit of renaming your measurement values. This is V in. V in. This one is I for current. This one is V out or V load. V VL. L for load. I think we are good to go. This one is a half wave rectification. In power electronics, we don't use solver. Just note that we can't use a solver. You can say the solver doesn't connect to any branch in power electronics. What you use, you go to back to library, you go to specialized power systems, use power GUI. This one, you select that power GUI. This one is our solver. It acts like our solver. Then you double click there. It has about 4 simulation types. You have continuous, discrete. These are the commonly used. For the discrete is where you provide a sample time. It has sample time. Let's use the default for now. You can go to help to understand this solver, but yeah, just in case you need to know more about the solver. Therefore, just say okay. We have used our diode, that is a forward biased diode. Then we have used current measurements and voltage measurements to display our scope. Let's run and see what happens. Before I run, double click on the scope. Right now you are using one graph, but you have three. Therefore, you have to select three, use the gear icon here. For the layout, select three. For them to be three, then say okay. Now we have three, one for I, V in, VL. Then you can run. Double click on the scope, maximize, because if you want to view closely, you go to zoom in section, you select the zoom X. You want to zoom along X, okay? Then you yeah. As you can see, the V in is a sine wave, but V out becomes a half sine wave. The bottom section is we don't have the bottom section. You can see you don't have a bottom section. You only have a positive section because this top section is a forward bias, reverse bias that we are not using. That's how diode is used in half wave rectification. Just to be curious, let me delete this diode and rotate this diode like that. Let's see what happens. Run again. Compiling, okay. Let's go back. Let me zoom here, but you can't be able to see. Let me go to the icon here. Scaling, want to do auto, apply a scale auto, so that you can be able to see. As you can see now, after rotating my diode, this is my V in is still a sine wave, but you see now the top section is eliminated. We remain with the bottom section. Therefore, that's the reason why it is called a half wave rectification, because it eliminates one half of a sine wave. In my next video, I will now illustrate how you can use diode for full wave rectification. Thank you. Share the video, like and comment, subscribe. That's very important. It motivates me to make more videos. See you in my next video where we are going to discuss full wave rectification. Thank you.